My watch says 3 o'clock, so I guess it's time to start. And it's time to welcome you to this epic online technology meeting on additive manufacturing of metal and its application. My name is Francesca Moglia. I am the laser expert in EPIC, and I'm here with another very good expert of mine and my colleague, Antonio. So Antonio, maybe you want to say, you say he's waving his hands.
Good afternoon, everybody.
Very good. Thanks a lot, Antonio. So we give now a bit of introduction to the topic and a bit of introduction to, and this is coming at best with this. So this is actually this one. So this is a bit of the first slide, maybe the banner that you saw or on our social media presenting this meeting. This shows also the sponsor of this event, so Zeus MicroOptics, Avantes, and OPTOMAN. But now is not the time to tell much about them, because I wanted to just say these are 3 fantastic companies belonging to the EPIC network. That is actually this one. So these 3 little logos you saw before, they are now even smaller in this big bunch of logos that are representing actually at the moment the more than 750 members of EPIC. So they are all together, and we are keeping them together to basically strengthen the ecosystem of photonics, and especially in Europe. And how we do this is basically through this team that you see here. So on the left side, you see what is EPIC about. So like a bit of important words, like keywords for EPIC. And on the other side, you see these 13 people that are actually trying to make all these things real. And what I mean with real means that we have a block of activities that is the one that is now blue. So technology, access to markets, and market reports is a bit more the technical part. This is the thing that this team of people, so these 6 in the rounds, so me and Antonio, you saw us already, but also the other 4 colleagues of ours are helping in basically talking about technology with the members. So we do really a tailored work with you as an EPIC member to talk about your challenges. It could be supply chain, it could be the market application, it could be something confidential, and we keep it confidential for you, and we try to support you in this way. So also we buy market reports, so the access to markets is also given by real market data that we really buy from the usual suppliers. But then since more than a year, we have also our colleague Tracy that is also in the round. She's really helping us to making really market and data market reports that are only for EPIC members and are only on specific hot topic that we recognize that are really fundamental for the photonics world and for our members. And so that's why we focus on this, and we try to really go deeper into some of these topics with the help of Tracy and some of the advisors we have. Then there is also a world of events and of marketing that is also would not happen if these other 5 people here in the circle wouldn't be there. So we help a lot. So this is a technology meeting. Of course, we talk about technology, but we have also event manager behind the scenes that are doing a lot of work. We're also doing more networking event closer, for example, to typical exhibitions that are important for photonics. We do also events in person that we are soon start to do again. But also we do also marketing support to the members with specific actions on our social media, on our website. So this is something also that we do tailored for our members, and with the help of these 5 people as well. Then the last block is basically mentorship. For this, nobody is responsible. It's still red because it's you, actually. We have more than 100 members. So people in the members that are really supporting other less experienced ones. So mentor-mentee relationship is something that we are helping in EPIC. And also Carlos is now in the circle. Our CEO is the one more responsible for investment. So we try to bring investors closer to the photonics industry in EPIC, and is also the one taking care that all your positions open. So all the people you're looking for and that are basically listed on your website are also listed in jobsinphotonics.com. That is this big platform where we try to help this HR issue that we know the technology and this industry has in finding the right people to be hired. So this is something also that EPIC is doing, and Carlos is helping. Then Ulrike is also there, is not in a circle because she's also working behind the scene even more than you can imagine, but she's our COO and she's helping in all of this that I said so far. Now, going back to our calendar. So this is our EPIC Online Technology Meeting calendar. As you see here, we are at the 6th meeting, and there is something coming up again that I want to maybe specify better here. So if you are still maybe belonging to the process monitoring system, and maybe you're also interested into the meeting that we have next week about agri-photonics, or the one at the 30th of May on photonics for woodworking. But then I know that some of you are also interested more in smaller lasers, smaller application, micro-optics, micro lasers, and this is maybe the LiDAR miniaturization meeting on 9th of May, something relevant for you. But then I have something that is even more relevant for all of you I know here in the room, and is this other box on the side. So we, as I said at the beginning, we are studied again to really meet also in person, technology meetings. That's something that after the pandemic is now a time to restart. And there is something that is really relevant for you. So a 3D printing of metal event at Siemens Energy in Finspång in Sweden. So that's what we want to do on 8th and 9th of June. So keep it on your agenda, keep it in mind, because there we want to really talk about technology, not only like here in the Zoom room, but also in person in Sweden. So please take this on your agenda and feel free to reach out to me also to find out how to join this meeting. And this is in a red box, is also saying to us, if you want to push really some meetings, some topics that you would really talk about and you have a lot of challenges, please reach out and we can add it also to the calendar that is actually getting richer till the end of the year. We will announce soon more events. Now, here is time to talk about our actually sponsors of this event. As I said at the beginning, we start with Avantes. Avantes is really enabling the spectroscopy solution for also additive manufacturing, also integrating very complex spectrometers. Then we have OPTOMAN, so specialists of coating, especially for those challenging coatings for laser optics where high power and high energy pulses are really there. And so that is where you should go if you want a super resistant coating. But then there is also SUS MicroOptics, so our expert for high quality refractive and diffractive optics, so on the micro size. And so for this is possible for every application, so additive manufacturing, but also automotive, photolithography, also the silicon photonics, and many more. And so these are our three guys today. They keep in mind that this additive manufacturing of metal is something relevant for them. So then, of course, we have the idea is this meeting is made for building business relationships. So if you manage yourself in this during the 2 hours of reach out to each other, please do it. But if you cannot, you feel free to reach us via email to me and Antonio. So francesca.moglia@epic-assoc.com or antonius.raspa is the equivalent one, and you can reach to both of us and try to get support and connect to someone that you maybe couldn't discuss with or you couldn't reach by chat in this call. We are also reachable on LinkedIn, so Francesca Moglia, Antonio Raspa is also easy to find. And also for all of you that are now on YouTube, you are probably either watching the streaming that we just started, or you are watching it in a recording of this meeting. You are also free to basically reach out to us, to the two of us, and then we can connect you to the people that were here in the room or are in the room, but you're not directly here with us, so it's not possible for you. But if you are live in the streaming, feel free to ask questions as well, because we will try to involve you in the discussion as well. So now we get closer to the topic of this meeting, and we have the agenda here. But maybe we have Antonio here that want to tell about a couple of words about these guys and ladies that we have today speaking. Right, Antonio?
Yes, thank you, Francesca. Okay, so this afternoon we will have a very interesting conversation on additive manufacturing of metal and its application. We will do this conversation starting with a presentation from Christian Schröter, the CSO from Optoprim, who will the support and the cooperation of Florian Eibl, the CTO of Cognitive 3D, will show us a very interesting success story about the cooperation, because this is the key word of this meeting, the cooperation. Then we will go to Mandaná Moshiri, the Senior Technology Manager of the LEGO Group. I think that there is not necessary to say more about the LEGO Group. And then we proceed with machine builder and system integrator, and we will talk about the system from LUNOVU, thanking to Rainer Beccard, the Managing Director, and the system from Meltio with Brian Matthews, the CTO. But that's not all. We have a lot of other people in the room. Francesca, who we have in the room?
Thanks a lot, Antonio. Yes, so that is what we really like to say. At the beginning, we mention only the speakers, but then we see who is in the background and is willing actually to cooperate also with the speakers and among each other. So these slides represent all the people that sign up for this meeting. And basically, if you look at it yourself, it represents really the full value chain of the topic additive manufacturing and its application. Because we start with some end user. As you heard, we have Mandy here from the Lego group about more consumer goods, but we have also other people around in this room also talking probably about energy application, about aeronautics, consumer electronics, or other machineries, and also lighting. So this is also something that keep in mind. These are the guys here, and maybe who knows who is on YouTube. But then also who is really important, we saw already someone of you will speak as machine builder, but some of you are just in the room. These are all the people that sign up also from the machine builder side. That is of course a core part, because you are basically creating the technology, but you need also help from your supply chain, looking at your end users. Then there is something that I really consider very important for this for this technology, the additive manufacturing of metal, and is the job shop people. So you are basically those having some machines. Some of you can maybe even edit or add to the machine, but most of what you're doing usually is to listen to your customers. So you know exactly what customers in different application fields know and want. And so that is why you are the one also knowing and being able to talk a lot in this room and ask for the challenges also of your customers. Then there is process and services. We have also there a very large representation. Some of you are experts in metal additive manufacturing specifically, and others are here, but they have also a lot of experience in generally in laser-based advanced manufacturing, not only additive maybe. And then of course, who is the rest? Well, the rest is what is behind the scenes. So laser manufacturers that are probably interested in how they can implement their lasers, or maybe who knows also for process monitoring, or for the real additive manufacturing, or just maybe you need additive manufacturing, who knows. Then we have a lot of course, optics and micro-optics, filter and coatings, but then process monitoring system. We know this is a must in many industrial processes at the moment. So I believe there will be a lot of talking about also this in this meeting. And then all down to beam shaping, very important. We hear also the first topic. Equipment, advanced materials, very important. Also considering the metal powder here is really the basic. Without this, we cannot work. And then the R&D, because of talking about the additive manufacturing of now is a thing, but talking about additive manufacturing of the future is also very important. So what is the R&D represented here? Now, we maybe talk too much. Antonio didn't, but I did, I know. So it's time to give the floor to the first speaker. So this is back to the agenda. It's a real pleasure to welcome here Christian Schröter from Optoprim. Let me spend a couple of words about him, because he's really the one that understood the spirit of this meeting and the idea behind EPIC of building collaboration. So he brought here a threefold success story. I guess a case of uniqueness of this kind. So I'm really happy to welcome and give the floor to Christian Schröter from Optoprim. So the floor and the attention, everyone, goes to you.
Thank you very much, Francesca. Thank you for the nice introduction. Hello to everybody. Yeah, it's a pleasure to have the presentation to you together. And yeah, we start as announced with a topic called beam shaping in the additive. First of all, my name is Christian Schröter. I'm from Optoprim, sales director, as announced by Antonio. Thanks for that. And so let's start. Today's topic is AFX beam control technology, lasers built for AM series production. And here a small agenda. I start with a short introduction of Optoprim and nLight, also some background by two companies, then the AFX introduction and the motivation, the technology, and then some public examples of applications. So Optoprim is a distributor for industrial and scientific state-of-the-art laser and photonic products. We are founded in 1994, have 65 employees, have locations in France and Paris, in Germany and Munich, and 2 locations in Italy, in Monza and in Rome, and have a strong focus on industrial laser applications and material processing. We're offering sales, application, training, service, and support, and very important, we are a member of the EPIC network, which we are very proud of. So distributor means maybe short note on that. So we have principals from suppliers from all over the world and represent them here in our regions, from laser sources to optics to process monitoring, basically a lot of components along the strengths of a laser-based machine. Then here a quick overview of our applications lab, as we are also working on the processes with our customers. So from macro to micro to marking processes, we try to have different laser technologies to approach the application as best as possible with the right technology. So using different types of lasers, for example, different types of optics, and we have the analysis equipment as well. And then in general, industrial processes need industrial service. So we do support, training, application support in our lab or on customer side. We have the field service, customer service in general, and also remote service, spare parts. And we also do consulting for laser setups or maybe choosing the right technology for the process of our customers. Then the second company I want to introduce real quick is also one of our principals, is nLight. It's a fiber laser manufacturer from US. We work with them for more than 20 years with our group. And they are a vertical integrated leading supplier of high power semiconductor fiber lasers. And there are some facts, let's say, in which applications area they are around, when they have been founded. But the most important or interesting part, I think, is really to see the vertical integration on the bottom right, which means from the semiconductor, then the semiconductor laser, so the pump modules, basically, the optical fiber, and then the fiber laser. So, and this brings me already to the topic. We have here a special laser, which called AFX. So AFX is an industrial fiber laser with a rapidly tunable beam profile, which is optimized, for example, for additive manufacturing. So you can see the different beam profiles which the laser can offer. And on the right, you have the 19-inch rack mount laser, where all these beam profiles are enabled directly from the fiber. So the motivation why we have, or nLight has developed such a laser, is the material processing performance really depends on the laser beam characteristics. So typically parameters is the size of the beam, the shape, and the divergence. And the precise heat deposition is critical for controlling these feature sizes, maximizing the production rate, maximizing part quality, then minimizing heat affected zones, spatter, porosity, and other, say, effects which are within the process. Then also versatility of materials or compositions of materials and thicknesses are the challenges or where the motivations. And this technology now is here on a single mode laser up to 1 kilowatt. And we have this technology also used for other applications. So for cutting, for example, or for welding, it's a proven technology up to 18 kilowatt. And it works pretty well. And as we said, it's like different improvements for your process. Then why we need such a technology for the AM tools? So what is important? So we have this spatial beam control. So one thing is the standard laser machines are used usually with a single mode laser, as you can compare with a fine point paintbrush. And then others which have like thick layers and then want to really increase productivity, they have another laser inside, which is then a multi-mode laser, which is compared to like a thick paintbrush. So at the end, you have both features, and but at the end, with the laser technology up to now, you were not able to have both in one. So it was always the choice, one or the other. So as the parts have typically fine and large scale features, and the single mode laser has also a smaller spot size, and maybe also the productivity is less. We thought how we can combine it. So we decided to have everything in one, and so you have the full range of spot sizes, and on top of that, you have different beam shapes. So why different beam shapes? It's the question. Why additional to the different diameters, the beam shapes? So here you can see the different profiles of the standard single mode Gaussian beam. You have very large intensity in the center. Then with a flat top, it's already improved, and you see, let's say you have a wider, higher width of the beam, so you have maybe a more higher productivity already, but there's still quite a portion of intensity in the center, which is also not perfect for the process. And then comes the beam shape into the game, which makes it more interesting even. So you can see then on the bottom, the three cross sections, how that looks like with the individual beam shapes with the same diameter. So on the left, you have a little bit of balling effect. On the middle, it's almost a smooth, let's say, line we were able to achieve. And on the right is like a perfect shape. Also, if you think about stitching these different lines to each other, that kind of geometry is very beneficial. And other technologies, really, if you want to do this, they increase costs and complexity. And yeah, if you don't have this combination of higher width or more width and the beam shape, the decrease of the performance and the reliability is also one topic. And the ring really and the higher width is providing quite a benefit on this. So how does it work? So I want to introduce you a little bit to the, let's say, in a simple way, to the technology, how we can achieve the different beam shapes and have the different beam diameters. So what you need is basically, okay, you have the fiber laser, then three basic components. It's a feeding fiber with a multiple region or guiding regions. So we can have 2 or even 3. And then you have a fiber that enables the beam to be shifted radially via like a mechanical manipulation into the different regions. And it needs to be for sure also adjusted in a very fine detail. So on the bottom, you can see the resonator of the laser in a very simple way. Then you have this, let's say, call it AFX. CFX is our multi-mode product, the AFX beam shaping part. And then you have this multiple region guiding fiber with the multiple guiding regions. And there on the right, you can see how we basically do it. So it's like from the center in the core, we shift it step by step from the inner part to the outer part. And that ends up, you will see it later on in another slide, into different beam profiles. And we can do that in a very fine scale. We usually have pre-programmed beam shapes, but yeah, we also can do something in the middle or can be very flexible with this technology. So in specifically on the AFX, here's some facts about it. So the AFX technology in the fiber laser, it really maintains all of the fiber laser performance and reliability benefits. There are no free space optics. It's very fast switching. Also during the process on the fly, it's very reliable. We have done like a 20 million cycle test of changing the beam profiles and have same performance of all our beam profiles. And a very large benefit compared to other technologies is a large depth of field or a large depth of focus, which gives you another advantage of high stability of your process. So how that works, here's a small and easy animation. So you turn on the laser and from the laser directly, you see switching the different beam profiles at full power on the fly. So you can get from a Gaussian beam to like a settle mode to a full ring mode, and you can shift it step by step, the power from the inner to the outer side. Then back to the applications. In general, we try to increase precision or to improve precision, optimization in general, and productivity of the AM process in the powder bed. And that's all for lattice structures, so for fine structures, for mixed geometries, and for bulk geometries. And how does it work? It's basically using the different beam diameters, which you can see on the bottom. So the spot size 0 is a standard Gaussian beam. To the bottom right here, the ring mode, which is then the width, the beam profile with the biggest width. And then additionally, you have this beam shapes, and they have very beneficial properties for the process. And so you can tune from very fine scale to bulky parts or in between only by switching on the fly your beam profiles on demand. So here's a first example. So we show here some public examples. In this case, it's from Fraunhofer ILT. They have an AFX laser in one of their machines. They did some tests on Inconel 625. And what they were showing here is like a reference parameter of a standard powder bed fusion machine, then a maximum scan speed and a maximum build-up rate based on beam shaping. So the reference parameter is with index 0, standard power, relative standard speed, and 50 micron layer thickness. And then with the maximum speed, they try to see where they can get with the beam shaping to which kind of maximum speed. So they ended up in 2,200 millimeter per second, which is already twice than before. And then they also tested the max productivity. So that was a combination of more power, more speed, and higher layer thickness. So they used here 100 micron of layer thickness. And you can see in the bottom that between 6 cubic millimeter per second to 70 cubic millimeter per second, it's quite a difference. So almost factor of 3 for the material Inconel 625, and still at a density of 99.8%, which is a very high standard, and also the requirement of the industry here. Then another example is from Fraunhofer IAPT in Hamburg. They did some tests with the processing of ILSI 10mg, where they used the donor profile to enable higher energy input, especially compared to a Gaussian profile where you have in the peak, it would lead to much more too high laser intensities. And they found, or their summary was that they can build parts with a higher build rate almost by 103 cubic centimeters per hour, which is another example for almost a factor of 3, and still keeping the high density. They see still further potentials of reducing the density and then improve the productivity, or even use higher layer thickness for this aluminum material. Last example is from the Technical University in Munich. It's a processing of 360L. It's they have seen with their tests and the experiments and researches that they can extend the process window quite large in terms of more power and higher scan speeds. They have, so that also ends up in an increase of productivity, then the reduction of balling effect, and tailoring the microstructure. And this keyword, please keep in mind, we will hear something very soon about it. So maybe here also see the beam profiles on the bottom right, which really you can see it's to match them and stitch them for layer by layer and line by line. It's really a beneficial shape, and that's all thanks to the donor profile you have here. So as a small conclusion or summary, so the AFX is a breakthrough in laser powder bed fusion tools. It provides unmatched productivity and part quality. It enables a new generation of AM tools for serious production, thanks to their benefits. And then this novel technology is like, industrial leading at the moment. We have, with this optimized beam shapes, everything is beam tuning on the fly for each process step, basically. And you still have this all-in fiber design, where you overcome limitations of previous technologies. And if you want to learn more, please feel free, go on YouTube. There are, from our Formnext presentations, a lot of talks from the different institutes, and also from Aconity and some other partners, or on our web pages at Optoprim or at Enlight. So now back to the keyword, tailoring microstructure. So the next level of tailoring microstructure, in general, maybe the next level of 3D printing. How about 4D printing? And that's the word already, or that's the word where I'm going to overhand to our partner and customer, Florian from Aconity, because he's now catching up on the topic, plus some general, let's say, activities what Aconity is doing. Thanks for your attention, and please feel free to ask any questions you have.
Thanks a lot, Christian. Let's say with this slide that you left at the end, let's do like this. Let's give the floor directly, because everybody I know wants to hear about 4D printing. And then we catch up with the both of you at the end of Florian talk. Are you satisfied with this option?
Yeah,
because we cannot keep these people waiting longer. So Florian, thanks a lot for being here. Thanks a lot for joining today and for reaching out when Christian was talking to you and accepting this invitation. I'm really happy to have you here. The floor is already yours, so I just mute myself. Please, Florian.
All right, then. Yeah, thanks a lot for the introduction, especially to you, Christian. I hope everybody can see my screen and my pointer as well. So what I want to do in the next minutes is, thanks. Yeah, I hope to be able to give you a better understanding of what this beam shaping, the reinvented beam shaping that just saw, can give us in terms of LPBF processing. So for a start, I think most of you know that laser powder bed fusion is not a simple process, and it is in fact not a single process. So there are many partially complex interactions and sub-processes taking part. I'm not going to go too much into detail there, but there is a lot happening in and around the melt pool. And in the end of the day, all of these processes define the shape and the size of our melt pool, as well as the solidification conditions. That means if we look at our final part, the material properties, especially mechanical properties, as well as part quality, being detail resolution, density, and surface quality, are more or less defined by the outcome of this complex interaction. And so far, we as machine manufacturers or as machine operators, the like, we are somewhat limited in what we can do to influence this process, because typically we are dealing with a somewhat narrow process window. But with the technology that Christian just showed, it is possible to add the intensity distribution as a process parameter. And we already saw that we basically do no longer have just a single laser, but we have more or less 6 lasers at our hands, where we can choose from a single Gaussian beam to a ring mode beam with more or less 3 times the size, and certain steps in between. And this allows us to deal with intensity distribution the same way as we do with scanning speed, with spot size, with laser power, with modulation. So basically to just use it as a variable process parameter to optimize the process towards our application. And those of you who have already done process development with a single machine already know that it can be a substantial amount of work to just do that for one parameter set or one laser beam source. And now we have 6 of them, so we need to start somewhere, which is why we did quite an extensive study with Inconel 718. We used our largest machine so far to print many samples in one run. And we carried out 6 runs with 180 parameter combinations each, leaving us with slightly more than 1,000 different parameter combinations that are going to be analyzed in further detail. So what we did, that's something important to keep in mind to make that a more fair comparison. Since the ring mode is always a bit larger than the Gaussian beam, we defocused the Gaussian beam so that it has a similar spot diameter than the ring mode, so that we are not looking at different spot diameters, but more directly comparing the different intensity distributions. And the first step that we did was that we looked at the processing windows, where we basically plot the outcome of our processing over the laser power and the scanning speed. And we categorized those parts into several categories. So the black axis show parts that have not been built successfully, where we had to cancel the process for those parts in particular. The blue crosses indicate parts that can be built up in a stable manner. And last but not least, the green circles show parts that have a density of greater than 99.5%. And if you remember the image from the slide before, it is a somewhat brutal process layout. So it is, of course, possible that we have some cross correlations, that adjacent parts influence the outcome on their neighbors. But nevertheless, this effect is the same for all combinations that we looked at. So we still can compare those results to each other. And what we see here is that the processing window for the ring mode beam is somewhat enlarged, especially in the area with the greater energy input. So that means that we have less instabilities due to overheating, which can, of course, be explained by the absence of the peak intensity in the middle of the ring compared to the Gaussian beam. But that result also encouraged us to look more towards the other end of the processing window, meaning can we exploit this increased stability towards greater scanning speeds? And while this was not the core topic of this investigation, we still saw some promising results. And as you can see from Christian's results, there is, of course, the possibility to apply these intensity distributions to greater scanning speeds as well. But the most interesting part of our study was the following. So we selected one parameter that worked well for all different index settings, meaning intensity distributions. And we saw that in static tensile tests, we do not only see a greater tensile strength for the samples built up with the ring mode intensity distribution, but we also see that at the same point, the elongation at break, meaning the elasticity of the samples, went up significantly. So typically, you cannot have both at the same time, but in this case, that was possible. And we then did extensive metallographic work to find the reason for this, basically. And we didn't really get to a conclusion quite quickly. So we saw that the microstructure looked similar, where the primary dendrite arm spacing was quite similar, no difference in segregation behavior. But at some point, we did an EBSD analysis, meaning that we looked at the texture. And at the left-hand side, you can see the results of the EBSD for samples built with the Gaussian intensity distribution. And at the right-hand side, you can see the texture of samples produced with the ring mode. So that means that we can clearly see a somewhat chaotic crystal growth orientation on the left-hand side and a very structured or sharp texture with the preferential grain growth orientation for the index 6. And together with our partners, we then found out that this is most likely directly correlated to the melt pool shape, where we can force the crystallographic structure to grow into the direction of heat flow, which we can influence with the intensity distribution. So in the end of the day, this enables us to directly influence the solidification conditions and thus the mechanical properties of our part, in addition to a generally increased melting crack stability and less spatter production. And since it can be shifted quickly without the requirement of any additional optics, this is possible within build shops, of course, but also within individual layers, but also within individual vectors, if you want. So to conclude my talk, basically what I just presented is the solution. This is also what we can provide. And what we need or what we hope to gain from that community is the problem. So if you have any part that might benefit from that possibility and you're able to share it, please reach out to us, get in contact with us. We want to see this solution being applied in practice. Thank you.
Thank you very much, Florian. Thanks a lot for this concluding these success stories with Christian. So now it's maybe time for you to think about some questions. I see you are still not warm enough, but it's time for me to ask what we call the epic questions. So the epic questions are, what can you do for them and what can they do for you? meaning that them is the photonics community, the people here in the room about additive manufacturing of metal. So we start with Christian because he knows the community very well. And so Christian, what is, maybe we talk about Optoprim, if you know some, of course, challenges that Enlight has, but of course we talk about how we can collaborate with Optoprim more, also concerning your maybe labs that you have.
Yeah, so that's a very good question. So first of all, what we are basically, how we can cooperate. One thing is what we always love is like innovative products. We are a distributor here in Central Europe. We want to have, yeah, if somebody is looking for sales representatives and technology innovation driven sales applications and service representatives. So if somebody has unique products and needs somebody in France, in Italy, in Germany, we are very interested to such discussions, and also dedicated to additive manufacturing. As you have seen, we're already collaborating with different institutions. So if somebody has ideas based on the beam shapes for the Enlight laser, we would be very pleased to push further materials, properties, whatever. If you are like an institution, if you're a machine builder, if you're end user, everybody is welcome who has interest. We want to understand the needs, and then also, yeah, providing maybe new products, but also new ways of working on it. And yeah, what we can provide is, as I said, as we are not only want to be representative of innovative products, we also have them as principles. So from laser sources to optics to process monitoring, all of one hand. And then additional on top, we can do the process development in our applications lab in Monza. We have all the different laser sources, different wavelengths, pulse, CW, yeah, whatever is needed for the application. And that's usually the approach how we address the customer's needs, not using the same hammer, only lighter or more intense. We really want to see what is the best tool for your process.
Thanks a lot, Christian. That was a good overview of what Optoprim can do for you, and also you can get from them. But now back to Florian. So Florian, you solved already a couple of issues, and you improved definitely the quality of the manufacturing with the help of Enlight and Optoprim support. What is that is still open, or what is it that you are interested in for collaborations, a part of what we heard today?
All right, so let's start with what is still left to do. And I think there was also one question in the chat that directly addresses what's still left to do.
Perfect, yeah, laser components, yeah, thank you.
And yeah, we saw that basically right now we compared the tensor results in build direction. And of course, the anisotropy is an open question, and what I just showed you was the result of the first 1,000 samples that we built, and last week we finished the second set of samples. So we will all keep you posted on the results for different build directions, and also different layer thicknesses and different materials. So we now have the blueprint of a methodology to assess the different technologies or the different possibilities of this technology. And of course, we are then flexible enough to quickly adapt to different materials or different applications. And to answer the question, how can we cooperate more? As you might know, we are a machine manufacturer, but we also see ourselves as a special equipment provider. So that means one question in the chat was if we are planning to implement an OCT sensor. Yes, if you want us to, you can get a machine with an OCT sensor, of course. But also if you have a specific application in mind where you want us to try out the effects of laser intensity distributions or multi-spot processing strategies, preheating and stuff, this is something that we offer besides the machine sales alone. And of course, what you can also do is that we together with the customer find out what the correct or the best working machine configuration might be for that specific problem that you have. And again, open question, if somebody has a part where he wants to implement locally different material properties, then we are very happy to find out if we can achieve that for a practical application, a large scale part.
Perfect. Thanks a lot, Florian. Multitasking with the chat. You are a Zoom expert. Thank you for answering already the question. Maybe we give a bit of floor of the people who ask the questions so that they can maybe introduce themselves. So Stefan, maybe we start with you, laser components. Thank you for joining here. So yours was the OCT question. Maybe you can say a couple of words about you and the interest in this meeting, please.
So thank you for introduction. My name is Stefan Leindecker from Laser Components Germany, and my question was the OCT one. From the point of view of an optic laser manufacturer, it would be very interesting to know what future requirements you place on your optics. So, yeah, it was the question about the OCT system, and I think future process systems to documentate the process will be a very huge point, I think.
Okay, so Florian, do you have some also then? Okay, maybe also to say better, like so OCT was more connected to the optics part, right? So not necessarily on the OCT itself. So maybe Florian, do you have also some issues, maybe some challenges about the optics and the optics that you have implemented from the process monitoring, but also maybe the laser side, any optics that you have, we could summarize in a big, all the optics, let's say, if something comes to your mind that now is kind of pushing you or keeping up at night.
Yeah, so in general, the question about process monitoring or job report, as some call it, is a never-ending story, at least at this time. So the main question that possesses all of us at night is which defect can I detect with what sensor, how well? And so there is, I think, not the one single solution. But it always depends what kind of benefit do you get with a specific monitoring systems, be it photodiodes, pyrometers, thermal cameras, OCT, optical microphones. How much more does it cost, and how much does it increase your yield? Because you always need to find the sweet spot between how much better does microprocess get with a certain system. So it's very hard to tell for us what general requirements we have. Our main strategy is to be as flexible as possible so that we can adapt our system to the needs of a specific application as fast as possible. But of course, sensor ports on scanners are an important issue. Be quite quick in adapting the coating of specific optical components. When I look at your company, I know that we already engaged in that. So basically, flexibility is the A and O, as I would say, in that regard.
Thanks a lot, Florian, for addressing this. Yeah, so process monitoring, I know, and I knew I wanted to hear it from you as the first machine integrator, machine builder, because that is what I expected as well to be a hot topic, but you explained it pretty well. So it has to be effective, but also, still convenient for you to implement it. That's a clear statement. That's a very good one. And now maybe
economically, physically,
exactly.
Economically
convenient. Exactly. Then I maybe would like to ask then Alexander from KSB, who asked about the anisotropy and in which direction maybe Florian was measuring it. Maybe you can introduce yourself and tell a bit about KSB, what you're doing.
Hi, can you hear me?
Yes, we can.
Hi, yeah. Thank you for having me, and thank you for asking the question. So we do use additive manufacturing machines for our own purposes, and well, basically, of course, Gaussian laser beam shapings, and of course, we are also interested a lot in enhancing the productivity. And Christian and Florian already showed this quite impressive, and this is why, well, yeah, if you keep the costs down, more and more additive manufacturing will be adapted throughout the entire business, and this is, well, very interesting to get the costs down. And this is why we do many tests, also all kind of, for example, features comparing the build orientation, but all kind of other things in order to understand more the process what influences there are. Yeah, and this is why I asked the question. So thank you very much for answering this, Florian.
Very good. Thanks a lot. Thanks a lot for being here as well. And so now let's go on. Maybe we see Antonio has a question for Florian, I guess, or let's see for whom. Thank you, Antonio.
Yes, I have a curiosity or a question, let's say. I'm really impressed about the flexibility given by this beam shaping in the laser. So I'm really curious to understand if there is any influence or potential relation between the beam shape and the surface finishing on the parts, because this is a key element also to the cost of the part.
Yes, there is, but it's not in that case necessarily the intensity distribution per se. It's the different size. So if you have a ring mode with 3 times the diameter of the Gaussian beam, the surface quality will be decreasing, simply because you have a lot of latent heat going out and enabling the particle adhesion to the outside. So as Christian described, typically if you want to achieve high building rate and great surface quality in one process, that you switch between those beam profiles. So you use a small beam for filigree structures and the outer shell of the part, and use the larger beams or the ring mode intensity distributions for the rest. And the challenging factor is not to melt more material in the same amount of time. That's quite easy. We can use a 5 kilowatt line laser and just use a millimeter of powder layer. But the challenge is to keep the differences in microstructure and mechanical properties in such combined processes as low as possible, because if you deal with heat treatment afterwards, heat treatment can be a nightmare to design if you have different microstructures present in the same part. So from our point of view, understanding how the intensity distributions affects the microstructure and how we can fine-tune the microstructure within a part is crucial to not only have greater melting rates on the paper or in data sheets, but also to put it into practice and use it in parts.
Thank you so much. Thank you so much.
Thank you. So thanks a lot. So we have, I guess, now really tackled all the let's say characteristic of this collaboration. But if you get something later on for them, for both Christian and Florian, of course, there's no, there is the possibility for sure to ask more questions. But maybe now I thank them again. So Christian and Florian, thank you so much. We go maybe on with the agenda, and it's the time for our, let's say, end user. Let's call her officially. Let's call Mandy from Lego Group the official end user speaking today. So it's really a pleasure to have you here today. I met you as an attendee of another event where you really were impressing me. So this is really a pleasure to have you here today, also to talk to the EPIC community and the extended network of EPIC. So please, Mandy, the floor and the attention of everyone goes to you and to Copenhagen, right? Oh, no, it's not Copenhagen, it's Denmark, but it's a smaller town, right?
Somewhere else, it's close to Finland. I'm actually sitting in Eibl, but in Jutland. But thank you very much. Let me share my screen. And yeah, okay. You can see it, right?
Yes,
everything is
all good.
Cool. Cool. Okay, awesome. Thank you very much, Francesca, for the introduction, and hello, everybody. This is actually the very first time I'm participating to an EPIC event, and I'm really impressed on how it is going so far. So I'm very happy to be here. In this presentation, I've tried to squeeze, like in a very short amount of time, a little bit about the company. I've collected some info about the Lego Group that you might not know. I will not really spend time telling you what we are doing, because I just assume that you know what the Lego Group is doing. And then I have the last slides about metal additive manufacturing, why we are using it, and some research areas. So just some general info is that the Lego Group is actually a family-owned company, and it's based in it's a Danish company, founded exactly 90 years ago. So this is our 19th anniversary. Our headquarters are based in this tiny town called Billund, which is in the southwestern of Denmark, in the region called Jutland. And it's the same town where actually Ole Kirk Christensen have founded the company. So we still have the original workshop where we actually collect now there all our archives. And the company is always passed from father to son now. The name Lego comes from two Danish word, lege godt, that means play well. So it's in our name, but also in our ideal. And our products are sold in more than 120 countries all around the world. And I have more than 20,000 colleagues worldwide. And today we are the most reputable brand, and according to the Time magazines, one of the top 100 influential companies, which makes all of us very humble and proud, because that's of course not something we take for granted. But moving to a more technical topic, I will tell you about metal additive manufacturing. And here I'm showing you 5 Lego sets. And there is something special here. All these 5 Lego sets have something specific in common. Some of their elements, some of their brick, have been molded on metal additively manufactured mold components. So actually this technology is supporting our journey to inspire and develop the builders of tomorrow. The main metal additive manufacturing technology that we are using today is laser powder bed fusion. And we use a specific type of steel material for producing specific components for the mold. The reason why we use metal additive manufacturing is for all the very well-known advantages given by this technology. I'm sure I'm not surprising any one of you if I'm saying that we are using it because of the design freedom additive manufacturing provides. For example, if we're talking about indeed mold components, the design freedom can be translated into conformal cooling channels inside our mold parts that improve the general thermal management on the mold. So this can be translated into benefits, for example, having a more uniform temperature. That means that the parts, the plastic parts will not distort, or decreasing cycle time, and so on. In this slide, I wanted to show you some research areas that we have listed for metal additive manufacturing. And the reason why we have listed these research areas is not because things are not working, but because we truly believe that you can always make things better. You can always make things more efficiently, and you can always make things more sustainably. So I don't think I will surprise any one of you with any of the box here that you can see, but I've just tried to split the different process. Again, in our department, in my job, we never look into a specific process. Our approach is always to the holistic value chain. And that's why I'm presenting you all the steps involved with the metal additive manufacturing process. So we have the pre-process that includes everything that goes from the design preparation, the job preparation, and so on. The process itself, so just the printing process. Post-process that covers both the, let's say, the removal of the parts from the machine, the cleaning up from the powder, the removal of support structure, cutting the parts from the build plate, heat treatment. But I'm also including in the post-process the final machining operations, because what we're printing is quite far from what is ready to be used for injection molding applications. If we think about the surface roughness, if we think about the dimensional tolerances, and so on. And then the last step, of course, is the final application. This is our goal. And thanks to the injection molding, we get our brick. So under the first step, I've listed some research ideas, because and one in particular, the design automation. It's because of a lot of steps that are done for designing mold components and for the job preparation are very repetitive steps that sometimes add very little value to the final product. And these steps can be automated if we think about new ways of doing designs. If we think about also, not conventional way for designing. Another thing that I'm still including inside the pre-process is a process simulation. And with process simulation, I don't think only of the printing process itself, but I'm trying to extend my view to the holistic process, to the full process chain until the parts is actually in the injection molding machine. And it's important to include this global overview, because that's the only way that we can achieve the holy grail of the first time right production by foreseeing defects. So, and within this wave of first time right production, there is also these things that has been mentioned also earlier about real-time monitoring. So how to not only to predict defect, and so if any predicted defects is actually escaped, or we couldn't predict this kind of defects, so that the monitoring can detect them and either stop the production or adjust it. So a sort of active monitoring. Then I've actually mentioned machine-to-machine repeatability, because given, oops, sorry, sorry for that. Given the complexity of these machines, sometimes it's difficult to ensure 100% repeatability between different machines. For example, if you buy two exact machines, it's quite common to find that there are little differences between each other. But given the complexity of the overall situation, then multi-material printing, because it's important that we start thinking that as we are thinking, for example, topology optimization, for example, putting material only when it's needed, we can also start thinking to put the right material or the best material where it's most needed. New technologies, because laser powder bed fusion, it's the main technology we use today, but we never know in the future. There are always new technologies coming out, new startups, so it's important to explore about how we can overcome current limitations. Post-process, for example, heat treatment, which is actually a very big step in the full process chain, and it's something extremely important because it influences the final performance of what you're producing. Automation, there are a lot of manual steps still in the powder cleaning, support removal, cutting the parts from the build plate, and so on, that can be automated. And also I'm mentioning here the final machining operations to help having a sort of smooth transition between the printed parts and the part that needs to go into machining. The two processes that should not be considered like close to different silos, but they're both used for the final product where we need to keep our attention on. And then I've added the new material explorations and new materials for injection molding, because our goal is to produce the best possible mold components, and they could be new material. Metal AM also enable new possibilities for material science. If we think, for example, of in situ composites and things like this that are just open to explore. And thank you very much for your attention. I'm sorry I kind of spoiled this slide, but yeah. You have here my email address, and you can find me also on LinkedIn if you would like to connect.
Thanks a lot, Mandy. Yes, the robot was asking for questions, but maybe we know it's you. Thank you. Thank you so much. I mean, I was expecting, because something really good, like some challenges, but this slide, this pink slide, I usually don't like pink, but this was like a massive one. So I guess even the people in the room are still shocked. No, but I see Mark he was relieved from this slide now with the robot, and now he can ask a question. So please, Mark from Carpenter Additive, please ask your question yourself to Mandy. Thank you.
Yeah, thanks ever so much, and pleased to meet you all. It's the first session I've ever joined for Epic, and it's, as the title, it's been pretty awesome actually. So I appreciate everybody sharing their knowledge and their experiences. Mandaná, it must be awesome to work for such a cool firm, right? I mean, trying to explain it to my kids and my family about, metal powders in an additive manufacturing world is too alien, sort of topics. When I mentioned it was in Lego, automatically they started to listen to me. So yeah, I think it's secretly a personal indulgence as well, as Lego is an awesome brand. So I'll get to the point where I'm trying to ask. What I want to hear from you is what we hear in the manufacturing businesses is that traditional cast molds are A, very expensive, B, very long in lead times. I just guess want to hear from you, has that improved how you have managed your internal moldings and costs, etc.? Has it been a positive impact?
Okay, so what is really important is that we look for the right technology for the right application. I don't believe it exists a one-size-fits-all technology. And even for molding, we need to look at what type of mold components in particular we are looking at, what's the complexity of this component, and can we improve the performance of this component with a higher complexity? And also how many times we expect to reuse this part. So there are a lot of, let's say, background questions we need to answer ourselves. Personally, I don't believe that, of course, metal AM can be applied everywhere, but there are a lot of areas where it can be applied and can also be an extreme and a great game changer. And a difficult thing here is the mindset, because when I was going to school, when I was going at university, additive manufacturing was just a one-day lesson in my entire degree. Like I studied material engineering, and I had one unique lesson within another course that was talking about additive manufacturing. So I've learned about the mindset growing up and studying by myself at work. But it's important that also we think for our future engineer at the university to start thinking additive, because it's a completely different ballgame. It's a completely different way of seeing things. And when you learn more about how to think additive, you can also see application that you have never thought before. So things will change also with new engineers, with more training, with more educations on this field. And also with AM, we are not even just talking about the machine, because the machine is just one step, one little step among the entire process chain. We are talking,
correct.
For example, there is a lot about the design, and I don't believe our engineers yet, at least in my hometown university, I can talk about that. I don't know about everywhere else in the world, but it's very important that universities start thinking much more about this kind of capabilities for the future engineers, for the future designers.
Yeah, no, thank you.
Thanks a lot. Yeah, thanks a lot, Mark. Did you want to add something?
To be fair, I was just, I attended Formnext in Frankfurt last year, and
Me too.
Yeah, I'm ashamed we didn't see each other, but maybe next time. And I actually did a couple of, we have a couple of powder head episodes, which are essentially just 30-minute chats. And we were saying exactly the same thing from an AM culture perspective, that it's funny, we everybody's got their isolated focus on the topics that are concerning them. So hardware guys stick to the hardware, metal guys stick to the metal side. So if we kind of step back and collaborate more, I think we'll actually accelerate the AM adoption. But I think at the moment, because the technology is still quite in its infancy, people are quite protective. They might be the next big thing in AM, so they're very fearful of, if they dare try to collaborate too much and share that, then it could be their demise. Maybe here end users can help, because us as an end user, we manufacture toys. We don't really care about the machine, the software, the hardware. We just want to produce the best possible quality toy.
Yeah, that's a good point. So it's really great that you accepted to join, Mandy, because that's exactly what also all the supply chain of the additive manufacturing wants to hear. So I know here in the room we have both power-based fusion and more like D&D, so laser-based D&D technology, so more for repairing. So I saw the comment of Jeremy from Sinova. So maybe we can ask the both manufacturers here in the room. If someone wants to comment also from the manufacturing side, from the machine builder side, what is power-based fusion that can support more, and also what the laser D&D technology can help. So this I let it open. And then maybe we ask Jeremy as well. But the thing is now, we have this pink slide again. I have to go back to that. So as we know.
Should I share it again?
Is it not? Oh, yeah, if you want, yes, for sure.
Please.
Because
Fantastic,
it's like
slide.
I have a screenshot. I confess, I have it, but maybe not
fine.
all of them have it. So it's really impressive, and I maybe can already start with an excitement for the process monitoring system. So we heard this topic already before from Florian from Aconity 3D as machine builder. We heard it from Mandy as well, but Mandy of course says I don't care. It does has to just to be working, and so she puts it on her slide because she knows that there's a lot of work behind it. Maybe we can ask someone that actually works on this that is in the room today. So we have Mark from Xenix, for example. What is your feeling, Mark, of this continuous talking about the process monitoring, and even in additive manufacturing of metal, of course? Can you give us maybe a hint of what you are doing and what is your interest in this meeting and in this pink slide?
Yes, hello, Francesca. Hello, everybody. Thank you very much. Yeah, I'm very interested in this pink slide because especially in the process and in the real-time monitoring part of the process. And I was a bit curious about how you do that, what is the benefit you get from it. Typically from Xenix, as we are infrared cameras manufacturer, our camera are used for real-time monitoring, or let's say after process inspection, but also what we feel could be the future is real-time monitoring during the process to, let's say, to monitor at best the laser characteristic to optimize the process in real time. So I don't know whether you have experience in this in the machine you are using for this kind of process.
Should I answer, or is it for the for the machine?
No, it's for you first, as you are
Okay, sorry.
as you are the user, but it's also
yes.
community.
So it's in our research focus because it's extremely important to have these things under control. Also because here is just you see just 2 blocks after printing, so it seems very short. But if we talk about the machining operations, all of that, we are talking about a lot of time and a lot of working hours, but by people like processing on the mold components that is printed. So defects can appear very much late in the value chain, and this is something we want to avoid. And so we need to build up the learning on how to detect them during the process while the process is happening. Because one thing is that you cannot do destructive tests on your finished part. And we are talking about steel, also technologies like CT scanning. And please, if CT is not one of my main experience specialist area, so if there is anyone else that knows more, please jump in. But I mean, with CT scanning, you cannot go too much in depth into a big block of steel, let's say so, or to detect very tiny defects into this big block of steel. So it's important to develop more real-time monitoring to support this quality assurance of our products.
Thank you very much.
Thanks a lot. Thanks a lot. So is there some machine builder who wants to comment? Because I have Harry there. So Harry, I pick you now as questions and comments from your side. Thanks a lot, Harry from Additive Industries. Please, the floor is yours with your comment and question.
Yes, hello everybody. My name is Harry Kleiden in business development in Additive Industries. Hello, Mandaná. Yeah, we met
Hi, Harry.
a few times in the past. Okay, yeah. In general, I have to tell you that the observations is actually also what we experienced specifically on the melt pool monitoring and data collection. Luckily, we have at this moment quite some tools which already gives us good data, reliable data, but then creating the correlation between that data and defects in your parts, that's what we are actually working on. But that's something we as an industry have to team up, and we as an it is partly application driven, it is partly equipment driven, but it's also partly driven by the design and of your parts. And so in that way, what we are doing is with customers, we use a Sigma Labs print-write 3D solution, which looks into the melt pool. With a number of customers, we have collaborations where we further investigate the behavior of the melt pool, and actually we make a thermal 3D image, and then correlate that to found defects. And in due time, this will come available for other customers. But yeah, anyhow, if somebody is interested to work together, and we are open to start a discussion on this. Hello.
Yes, I'm sorry. I couldn't
Yeah.
find the unmute button. It like disappeared. Thanks a lot, Harry. Yes. Thanks a lot for your contribution. Yeah. Open for discussion. So Harry is here. You have him. So you have maybe his email address later, or you can contact him on LinkedIn, and we are happy to help you also to talk to him. Thanks a lot for your contribution, your comments. And so the Lego world will get better, but also other applications are, of course, getting improvements if you work with Harry, probably. Thank you. So now we have a question from Antonio. Please, Antonio, ask your question.
Yes, thank you so much. Thank you so much for this great slide. Really, I'm still looking, and I think that for every box we can discuss for hours on each box. So I just make maybe a question asking if you can tell us something more about multi-material printing. So when you need or which are the purpose to change the material, and you are doing in process, so you are changing from one alloy to another alloy, or really? So tell us something more. I'm so curious about.
So for multi-material printing, this is actually a research area. So I put it here because as a background, I mentioned I'm a material engineer. So materials are very close to my heart. And I truly believe that we should not just think, as we were saying before, there is no one technology that fits all. There is not like we can optimize the design of components if we think about topology optimizations, lattice structures, and all of that. I also truly believe that we should look at the right material for the right application, but also if there is one application, the material that best fits that area, like if I have a mold component, I can look into area in which I want more or less, for example, thermal conductivity, and think about different type of material that I can use where I need more resistance, where I know that my mold component is to resist more loads, and other where I want more thermal conductivity. So I can look for another material that has a higher conductivity than the rest of the mold. So this is actually there because of my background. It's because I truly believe that it's important to keep in mind that we also tailor this, because there are technology out there that can already do this. Maybe some of them are different maturity level. So, but it's important that we keep in mind that there are researchers, there are startups, there are companies working on that. So it's important to keep in mind.
Very good.
Thank
Thanks
you so
a lot.
much.
Thank you. Thanks a lot. So I don't know if it was the multi-material or still this pink slide, but now we have two raised hands from machine builders. So that's very good. So first, Florian from Avantes 3D. We heard him before, but please, the floor is yours for the question.
It was not primarily a question, it's just an added information on the multi-material aspect. So there are several approaches out there. One of them is the one of the Belgian company Aerosent, where you have basically the application or the possibility of selective powder deposition. And as Mandaná said, they have different or various maturity levels, basically, because you're not doing process development for a single material, you are doing process development for especially the interface zone of two materials. And then you have basically all the options that you have squared, which means that especially we as a machine manufacturer, we do not think that we can solve all those open questions alone. Because think about us spending 2 years on developing one material combination, and then the first customer comes and says, nice, but I want something different. So again, here, if there are some applications in your mind or sample parts that just need to be tried out once, it is always possible to see how far we can get with the existing technology, especially in molding, if you think about some copper and tool steel combinations. But then it's a question of the resolution that you want to achieve in your part.
Thank you. That is a clear call for let's talk. So Mandy got it. She's smiling, and I guess Florian was his aim. So that is why we are here. So there is definitely room for talking about this, and it's true. The machine builder needs also some push. Otherwise, they don't feel like they have to do all the things or try one and then it's the wrong one. Totally understandable. Now let's see what Brian has to ask. Meltio, last speaker. So now it's nice to meet you already. Now, please, Brian, ask your question or comment.
Okay, thank you very much. Thank you for the presentation, Mandaná. That was really great to see. So yeah, my name is Brian Matthews. I'm the CTO of Meltio, and we've pioneered a multi-laser DED process. So your slide here is kind of interesting for us because I think we've been tackling these applications in an interesting way. First is that we've done a lot of applications for printing molds with conformal cooling channels like you described. But also multi-material. And I think what's interesting about DED, and you'll see some of this in my presentation that's coming up shortly, is that you have this sort of no contamination, cross-contamination in the process, especially with metal wire. So you have this ability to produce parts with multiple materials and not fight some of these technical challenges that you might see in a powder-based process. So that's something that we find very interesting. We've done a lot of applications recently with different materials, including tool steels, where we've changed materials in the part to improve the performance of the part. And that's something that we find really exciting. So that's something that's got a lot of traction inside the company. So I just wanted to share that, and I'll talk a little bit more about that in the presentation.
Very good. Thanks a lot, Brian. Yeah, this reminds me, we should stick to the agenda. Otherwise, thanks a lot, Mandaná, for your really interesting and exciting presentation with the pink slide. Obviously, is the highlight. Despite the robot at the end asking the questions was nice as well. The pink was overwhelming everybody. Thank you. Thanks also for all the comments. Let's go in order. So it's now time for another D&D technology, the one from LUNOVU. So it's really a pleasure to have here another success story. So it's really a pleasure to have here like a combined, let's say, presentation from LUNOVU and our also member Precitech. So please, Rainer, the time has come and the floor is yours.
Okay, thank you very much. Let me just try to switch over to my presentation.
Yes, I see it.
You can see it right now. Okay, perfect. So
hello to everyone. Mode, huh? We still need the presentation mode.
Oh, it's not on yet. Sorry. Okay, here it is.
Yeah.
All right, thanks. Yeah, thank you very much for introducing me, and also thank you for all for listening. So what I'm trying to do is I'm trying to introduce our DED, or we still stick to the LMD version technology, and the focus is a bit more on the let's say machine intelligence, or to what extent can we put intelligence into our machines or provide intelligent processes. Now, for all those of you who are not familiar with it, I mean, we've been hearing a lot about laser powder bed fusion. This is DED or LMD, which basically means we're talking about either wire or powder-based processes where we have a pretty high power laser beam source that's ranged between 1 kilowatt and 10 or up to maybe even 20 kilowatts. We supply the metal as a powder or as a wire. And if we do things right, we create a small melt pool that we can perfectly control. And if we move it across a part, we can deposit track by track and layer by layer very complex objects. And I fully agree with Brian. This is a technology that can already do multi-materials. It's perfectly suited for repair jobs, for modifications, as well as for really 3D printing from scratch. And part of my story is also about printing 3D objects on existing 3D parts that will come a bit later. Now, obviously, what we do as a company is we build these machines, and you can see some pictures here. It's CNC or robotic systems in various sizes. And actually today we do combine wire-based processes and powder processes, and some machines even combine both of them. Now, just to get some feeling for what is possible today, I mean, the powder process, the blown powder process is pretty old. It's like 20 years or so, but it has come to a very high degree of maturity. So we can print very different objects. And besides all this coding and repair stuff, we can build things like this here. This is a typical demo object consisting of 500 layers, pretty high, single wall with a very good control. Really close to the final shape. There's only a little bit of machining required afterwards. And yeah, more recently, we also went into the wire processes, and we actually do have a certain type of cooperation with Precitech. Now, what is really new about these wire processes is that they now have the capability to run in a multi-directional mode, which means it doesn't make any difference if you run back or forth and left or right, which has not been the case in the past. And that's due to a special design of these processing heads. And so actually what we do is we integrate them into our machines as much as we do the powder-based processing heads. Now, there are some advantages that people expect from the wire if you compare them with powder. So first of all, the material efficiency is high. It's always 100% because there's no powder that gets lost. And obviously, there's an expectation about lower material cost because producing the powder is pretty expensive because it's a complex process and wire is already available. So it really looks like processes can be much cheaper. And hopefully also people believe it can be more less risky in the operation because it's kind of a hazard-free, powder-free process. And what we do achieve is something like this here. This is also something we got from Precitech as a result. Build rates are maybe somewhat lower compared to powder, up to maybe 2 kilograms per hour, while the powder-based processes go up to 5 or 6 kilograms per hour. But what we can achieve is actually pretty similar achievements in terms of thin wheel structures like this one here. And I think these processes are approaching in terms of the performance through the next few years. Now, what is relevant from our point of view is really the process chain. And I already said it earlier, we try to put some intelligence into our machines. And I want to give you one example that shows you briefly what we mean with that. And this is about hybrid manufacturing. This is an example where we took a cast part, and the idea was really to take a standard cast part and do some customization on this part. So the idea was really, in order to reduce costs, just prepare a certain set of standard cast parts, put them into the shelves. And if the customer calls and says, well, I want to have type number ABC, they would like to literally print the kind of a 3D extension on the existing cast part overnight and then ship it. Well, what we wanted to do is really, we wanted to start with the cast part as it is. So we didn't want to accept any pre-machining. And that's why we introduced our scanning technology. So all of our machines come with an integrated 3D scanner. And you can see in this small picture, you can see a kind of a purple line that moves across the surface. And what it does, it generates a true 3D scan of the part. And as a result, we get this visualization of the scan. So we get a 3D model on the PC. And in the next step, we can load an additional geometry from CAD data. So we kind of merge these two worlds, the scan world of the existing part, which can be any arbitrary part without any CAD data, plus the CAD world. And we just merge them, bring them together, adjust the new extension on the existing part, and then run through the software, which does some slicing and toolpath calculation, and finally ends up with a work recipe or an NC code that's loaded onto the machine, and finally allows us to print directly on top of the part. And the trick is really that there's no manual programming required, and we can work on any kind of surface and print 3D on 3D. And this is what it finally looks like. You can see the flange that we've printed on top of the cast part. We could print it on any part of the surface. We don't need to prepare the surface. And if you you have to do the machining anyway after the cast part is done. And if you have done the final machining, you won't see a difference between the printed part and the initial part. And the other important thing is really you can print any material on top of the other one. So this is already where we can apply multi-material, we can apply graded materials, we can control material properties like grain structures or hardness or whatever you need for specific purposes. Now, I think the question that was raised by the organizers was really, what can the community do for us, and what can we do for the community? And that's what I want to answer here. So pretty much like the previous speaker, I want to emphasize we have an application lab that we run, and it's an open lab. So we try to open it to everyone. So what we expect from the community is really talk to us, come with crazy ideas. Nothing is too strange not to try it. And what we offer is actually our expertise in our lab and our machines to try things. So if you have a specific material or material combination or an application or a part you want to test, and maybe you've never done DED before and you don't really want to buy a machine at this time, you can just come and try, because we feel it's a very early stage in this development, especially if we talk about hybrid manufacturing, multi-materials and stuff like that. So the invitation is really, let's just try, talk to us, and let's see what we can do for you or what we can do together. And with that, I would like to thank you for listening.
Thank you so much. Very impressive. This we said that this technology looks extremely interesting and clever. And I see that we have already one raised hand from Jeremy from company Sinova. Please go ahead with your question.
Hi, Rainer. Thank you very much for this presentation. Can you hear me well?
Yes, that's perfect.
Very good. My question is regarding the DED platforms. I mean, essentially, most of the DED systems are installed today on standard milling platforms that are designed for rigidity. And do you find that the bottleneck when you're producing these shapes, do you find that the bottleneck is your ability to push materials through, or is it your ability to move faster in corners, for example, to prevent over deposition or overexposure? My question would be, in this case, would you benefit from a more dynamic machining platform in which to put your DED system?
No, not really. I mean, I have to say, what we actually do is we build our own machine platform, because the requirement is a bit different from a milling machine. It's not as fast and not as precise as the milling machine has to be. I mean, if we're talking about dynamic behavior, we're talking about a few meters per minute travel speed with very moderate acceleration, and so that's not really the key point. I think it's more the trick is really the combination of right mechanical design, control, and it's a lot about software. So our feeling is really that this process chain of how we control the processes is most relevant. Yeah, and that's why we've decided really to come up with something that is completely our own design. So we don't really rely on an existing platform, actually.
Good. Thank you for the answer.
Thank you so much. We have also Dirk Müller from Coherent that who raised the hands. Dirk, please make your question. I don't know if he's ready to talk. Maybe waiting for him, I give the floor to Laserline, to Windheim. Go ahead. Winddash, please talk.
I think they're still muted. I know.
Muted. Okay, this is because we are live, so
yeah.
Now it's no longer.
Now we can hear her. Now we can hear Windayesh.
Yeah. My question was that one of the primary bottlenecks for anybody who is trying to go into DED is finding the right set of parameters for one particular set of materials. Like if you want to deposit Inconel on, say, cast iron, or Inconel on Inconel 718, and it takes a lot of time, efforts, analysis to find the right kind of parameters, So how is LUNOVU trying to address that problem through intelligence, artificial intelligence? Are you providing? Because it's a very big part of doing any DED. And whether you are doing additive manufacturing or doing repair it takes a lot of time to set the parameters, correct parameters. Yeah.
Yeah, absolutely right. I mean, basically what we've done so far is we've set up a certain database for the typical materials we use, and we know a lot about how to adjust them for a specific part or a specific application. So it usually takes us like something like a day or so to do a basic process development or to adjust processes for a certain application. But you're absolutely right. Our long-term dream is really to apply some kind of artificial intelligence to run a huge database with all the know-how about materials and material combinations, finally allowing the machine to decide by itself which parameters are right to be used. But I think we have to say we're not yet there, no one's there yet. And there's a little bit of time, a little bit of effort to be spent, I think, I'm afraid, yes. But I think there is some progress. We're really seeing there's a lot of benefits from putting all the data into databases and really extracting the process parameters from the database, even today.
Okay. I saw that you have implemented a scanner also in your machine, and I think it is a very good, step for anybody who is trying to say remanufacture or repair a part, because it takes away a lot of programming efforts away from, and you can actually concentrate on the process.
Absolutely right. I mean, many of our machines go into mold manufacturing or mold repair or in general repair applications. And these people are always suffering from the fact that the parts they're working on have no CAD data, of course, because they're worn out. Yeah. So we always start with the scanning process. And in many cases, the time from scanning the part until the automatic execution of the process is just 5 minutes. And if you would do the same manually, you would spend hours basically, and you would still have a lower degree of precision in what you're doing. And that's one of the big benefits actually of the technology we run, this kind of integrated 3D scanning. Yeah, you're right.
Thank you, Rena.
Thank you. And okay, I try again to listen the question from Dirk Muller from Coherent. Can you make the question, Dirk? Oh.
He's lost.
No, he's lost. Okay, so we go back to Christian. Christian from Optoprim, go ahead.
Yeah, thank you. Hi, Rainer. I would like to know how interesting beam shaping would be for you for the powder DED, or if this is a topic you have already addressed in a way, or if you can think if especially regarding heat management and things like that, I would see some possibilities or improvements maybe.
I mean, we don't know yet. I mean, most of the processes run with top hat laser profiles because it's just direct diode lasers. Mm-hmm. And in many cases, it's what people really are looking for, a uniform distribution of the power. But we have built a machine right now, or it's already delivered, that is running a laser system with where the beam shape can be modulated. But it's still in an R&D phase. We don't know yet what the outcome will be. I mean, there could be a benefit in more complex systems if we switch between materials, if we switch between very thin structures and, let's say, more broad coating applications or so. But I think in the industrial area, it's not a topic yet, but it might be coming. Yes. Okay, because let's say if you remember maybe that one illustration where you saw the heat profile of the different shapes, the Gaussian beam, then the flat top, which you are using, and the ring, might be, let's say, with the ring, some more homogeneous way to implement the power into the powder. I would be very interested if there's room for collaboration to see. Sure. I mean, we just have to try, I think. Yeah. Yeah. Absolutely. Thank you.
Okay. I see Marcus. The great Marcus from Precitech, please.
Just a quick comment on the last question on beam shaping. So beam shaping makes sense. This is what we see nowadays in high-speed processes. This is why it makes sense in the LPBFP powder bed processes. The DED processes are slow processes. So there is no, and if we do printing of parts, we have very thin wall structures. So there is nothing left or right which can take the power, which can take the heat, and where we can distribute any kind of intensity or laser or temperature. So the temperature is in the track, it's in the single layer, and if we build layer onto layer, so the temperature is in there. So bringing any kind of intensity distribution is from my point of view, too much a waste of time and money.
So we need to try then, Markus, for you. Let's see who is right. Prove the concept.
No, we all. So as you have seen on the slides from Rainer, the wire head is already a head where we have a ring-shaped laser beam. So we have a ring-shaped intensity distribution. This is what we see. Okay, it's used for other purposes, but we can also discuss anything which relates to intensity distribution, to temperature distribution based on that ring shape, and we don't see any kind of benefit, as the only one is we can go in all directions.
Okay,
so
I think, or yeah, for the wire, it really makes, or you're already using it, but there it's like because of the optical setup, you're coming from the outside. But for the powder, I see still a more homogeneous treatment of heat and power into the material. So
you have to think about the following. Every powder particle has to be in contact with the laser before it hits the workpiece surface. And it has to be in contact with the laser everywhere. So if we have just a ring-shaped laser beam on the powder stream, there would be a lot of powder which would not get in any contact with the laser and would be completely destroying your powder efficiency.
Yeah. But as we have the flexibility to share the power.
Yeah. So I know you have the laser and you want to get the laser to the market, but I don't see.
You have the head, so but let's see. We will try.
No, you know what is this? Yeah, please, Rainer.
Maybe you can agree that we have to simply to find out. I mean, maybe there is a nice application where we can apply it, look into things that are not really the hot topic right now. So I think we should be open to everything. If we finally find out it doesn't make sense, okay, we've learned something, but maybe we find something nice, just trying it. So
exactly. And you know, Rainer, what is that the European Commission is trying to push? Exactly this. So if you don't know who to believe between Christian and Markus, you can actually try yourself, because now I show you something here that is what is called Pulsate. So Pulsate is an initiative that is, oops, sorry, here is the hidden, is an initiative that is given by the Commission. Basically, here is a bit the people there. So we have 6 competence centers, really expert in additive and advanced manufacturing. But of course, for today, let's talk about additive. Basically, what we can do for you is to, on the right side of the slide, give you money to try things. So there is 2 open calls. Basically, the one is called Technology Transfer Experiment that will open very soon. So April 2022 is the second one. You can come in 2 guys minimum, so or ladies or mixed, we all accept it. That means 1 technology provider and 1 end user. So if there is something that you want to check, like technological effort or improvement of your machine, you can always ask an end user or maybe an integrator to say, look, I have this technology, let's try it together and let's see. Let's apply for the money, we get under 50K, and for 13 months, we can try this. It could be beam shaping, it could be, is for D&D important or not? You can find out here. And also, if you're an end user and you're not sure yet at all if technology is like the additive manufacturing is something for you or not, you can apply for the adopter user case actually call that is running out actually on 31st of March. There you can apply a loan as a SME and as an end user and try to see, okay, is it D&D anything for me? Is it something that I can improve then my manufacturing part? For this, you get like feasibility studies, like it's a kind of a bit cheaper way, but it's basically given through the project, and you can get 25,000 euros and 3 months of project through this. So all your doubts can be clarified like this. And then on the left side, you can see all the possible offers that the Pulsate community provide for you. So also access to technical knowledge, that is of course all this consulting that we can do for you, also from the business side. Access to infrastructure, you see here, you can try power bed fusion or direct energy deposition yourself in our facilities. And then of course, assessment of digital maturity, software as a service as well, more the business part, trainings, community, and partnership is what we really offer. So if you have some doubts, of course, we support that you ask Marcus or Christian directly, but you can get even a bit of money for this. And so why not then go through this platform? And you know what? There is not only Pulsate. There is also another initiative that we have here in the room. So all ways to get to work together. And in this case, we have here Amires and also are you there? I see. Okay, Martina, yeah, you're there. So maybe it's the time to talk about Manuela as well, right?
Yep, I think you made a perfect introduction. So when you already mentioned some ways of funding or some ways of exploring additive manufacturing, and if it's something that you could benefit from, so I will try to share the screen. So can everyone see the presentation?
The slide is there.
Perfect. So I'm actually here on behalf of one Horizon 2020 project that is dealing with creating additive manufacturing metal pilot line. So the project started already in 2018. And the goal is to develop a pilot line that would offer like the full cycle of additive manufacturing of metals, including simulation, design, process control, characterization, and even the post-processing, post-treatment, and qualification. So the interesting part is that there are 20 partners in this project, and we have both the powder bed fusion laser beam and the electron beam machines. So there is really a lot to experiment with and to try. So within this project, we also have an open call, which calls for any companies, any individuals, anyone who is from the EU or associated country to apply for this open call, and you can receive up to 100,000 euros of costs covered. If you have any or any phase, any aspect of metal additive manufacturing that you would like to try, if you want to develop an idea, if you want to develop a prototype, if you want to assess materials, or improve process. So you are highly encouraged to apply to our open call, which actually ends at the end of May. So we are still looking for interested people or individuals, companies that want to apply. We actually have a webinar dedicated to this open call. If you want to join, it's tomorrow morning. And we have one company that already went through this process, and they will be sharing their success story. So if you want to know more, I can share the link afterwards, and you can join us tomorrow and we can talk more. So I think that's all I wanted to share very quick, but we are definitely interested in getting to know your projects.
Very good. Thanks a lot, Martina. So as you hear, basically, and so there is a lot of opportunity to work together, getting even a bit more of money of this, get services. And so you can work together. You can find out who is right, who is wrong, who is middle right, middle wrong. That is not the point, but the point is to find your final solution, the best compromise for the technology you want to provide and to use. So thanks a lot, Martina, as well. So reach out to her, to me directly. We can all facilitate the application to all the possible calls you heard today. So now it's time for, last but not least, We know him already. We heard him before, but now it's time to show his slide. He gave already some anticipation on the multi-material. So it's really time now to give the floor to Brian from Meltio. Thanks for being here, and the floor is yours. In presentation mode is even better. You regretted it now?
Thank you, everyone. Okay, let me start my slides here. And let me see if I can go in presentation mode. Hope you've seen that okay.
Yes, there you go.
Okay, perfect. So I know we haven't got much time, so I'm going to get through this like really fast. So I'm going to talk about Meltio. I'm the Chief Technology Officer of the company. Really what we want to do is to really bring down the cost of metal additive manufacturing, but also actually increase the quality. So lower cost and higher quality, that's really our driver to be a disruptor. The technology is about 6 years old. So we've incubated the technology for 6 years. It's a multi-laser architecture I'll show in a moment. But really, we've been a commercial entity for about 2 years. And the first sort of 6 months of that 2 years, we developed the systems, new factory. You can see an image at the bottom of this slide. And we've, in the last 18 months, we've really built the team. We have over 70 employees now. We have 115 systems sold. Over 100 are installed globally. We're in about 35 territories, countries around the world. So we're growing really fast. It's not been easy, but we're really happy with the progress. What we're trying to do is just to really tackle what I call that friction in the process from the end user perspective. So we want to remove those high upfront costs. And then really increase the capability in what you can do, not just small complex parts, but large complex parts and large simple geometries as well. So, and then multi-material is a really important area for us. So those are the things we're focused on. Wire is our 99% of our focus is in wire because of the benefits, and the presentation before me, Rainer eloquently described the benefits of working with metal wire. You use all the material ends up in the part. You've got a lower cost material feedstock, probably the lowest possible cost feedstock, and then also it's clean and safe to handle. So really that's where we've put our focus. Multi-metal printing is really interesting. So I'm going to talk a little bit about that. These are the 3 products we have in the market. We started with the M450 printer, which is great for universities. That was sort of our plan to start there and then sort of expand out. We've had great traction in the market with that product. And that allowed us to develop the Meltio engine, which we use to power CNC machines and robotic systems. And so that's really our product range. So from a manufacturing sense, it's like 2 products, but in the market, it's like 3 products because you've got those 2 flavors of the Meltio engine. The Meltio engine is actually the same product for CNC and robotics, except for the CNC integration, we have this thing called a deployment mechanism. That allows the laser head to motorize in and out, so you can do wet machining side by side with 3D printing, all in the same machine, and not worry about contamination or damage to hardware. And then the robotics, you don't have that deployment mechanism, so the head is all sort of permanently attached. So that's really the only difference. Here's a sort of a video from the M450 printer, just showing the process. And the thing to note is that just how clean the process is with wire. It's just wonderful. Just not just the substrate, but just the machine. If you look around the machine here, this is a machine that's been used at this point for several months of operation. And, you know, it's spotless. So for me, that's a really beautiful aspect. This is a titanium part, and we're just showing in a 3-axis system, and that is the M450 is a 3-axis system. We're showing that you can actually have pretty steep overhangs, you know, with no supports. Okay, and then the CNC integration, this describes what I said with the deployment mechanism, where we can deploy and retract the laser head automatically. Okay, I'll skip the other video because we're running short on time. Okay, and then robotics, a couple of videos here just to show how that kind of works, but I love the robotics. It gives you this sort of huge capability for complexity because of the dexterity of the robot for the multi-axis, and you can do these really large parts. Important to note, we've also developed really interesting software solutions for this. So you can do things like non-planar slicing, like you see on the right, which is not a simple thing to do because you're changing the amount of material you deposit circumferentially in that example. Okay. So really what we're trying to do is to give a solution where you can print a part really quickly with metal wire. The part shown on the left is kind of coarse because we have this nice flexibility where you can print really fine detail and work slower. Or if you just want to print a part really quickly because you're going to post-process it, and then you can go for a larger layer height like shown on the left. So we have that kind of flexibility for the end user. And really, that's just a simple process. I mentioned we work with wire. We can also do dual wire. The head is actually capable of blowing powder. That's not something we put a lot of effort into, to be honest, because wire just has so many benefits. But that's another unique characteristic of the technology. We've got an open materials platform similar to software. So if you buy the machine from us, you can work with any commercially available material. But we also offer our own materials just to allow the end user to benefit from our process knowledge with the different materials. We've just done a lot of testing, independent lab testing. We've demonstrated insanely high densities and other properties. Here's some examples. You can go to meltio3d.com and see these material properties on the data sheets. I mentioned something about working slow or working fast. So the part on the left is a TI64 part, grade 5, and that's as printed, not post-processed. And so most people don't believe that when they see that, because that's printed with metal wire. And the incredible resolution is shown with some of the undulations you see in the surface of the wings there. That's actually part of the CAD. So you can get this incredible detail with metal wire, which most people are really astonished to see. But the downside to that is that you're working slower. So that part was approximately 40 centimeters tall, and it took about 7 hours to print. But we could have printed that part in approximately 1.5 hours if we worked with a larger layer height, like you see on the right, which is a part we knew was going to be post-processed. So of course, the goal there is to have the minimum part production time. So you have that flexibility in the process, and we can work in that way. I mentioned multi-material, so we can actually work with more than one material in the same part. This was like a stress test we did, a Rubik's Cube. It was 2 different materials. I call it a stress test because there was 120 automatic wire changes in making this part. The wire change time is approximately 5 seconds. It's all automatic, and as you can see there from the stress test, the results of that is very good. Since then we've done a lot of real-world applications in multi-material. Turbine fan, this is a really good example. This was a simple example where we used a different material for the first few layers close to the substrate, so we can actually remove the part very easily because Inconel is harder to cut. But we've done applications like this where the leading edge of the blade is a different material, so you can get a harder wearing surface on the leading edge. And when you look at the machine finished part, you would never know there's more than one material in the part, which is kind of interesting. Then we've had more complicated multi-material parts where we've worked with materials that are magnetic properties. We recently finished a project to develop a part for a future rover for Mars, which had multi-material, which came out wonderful, which improved the metrics of the part from a performance and a characteristic, and especially for mass for a product like that. This is what we're trying to do. We're trying to get from research all the way over to real world manufacturing. We have a lot of actual production applications now, production customers. The reason we want to get there is because we really want to put thousands of machines per year into the market to have the disruptive effect we want to have. This year we believe we will sell over 200 machines. So we're getting there, but we've still got a long way to go. But the key to that is having the lowest part production cost and the machine being easy to use. Those are the 2 things that we believe are the most critical aspects to getting this sort of mass adoption. So here's some examples. I'll just point out things like the mold cores, and we've done a lot of injection mold applications with conforming cooling channels, including with metal wire prints. So that's a very interesting application for us. One of our customers actually bought into our technology just for that capability. So that's something that's really great with this technology. Here's some sort of before and afters, just examples of customer parts we've made. Again, some mold cores, like I mentioned, as printed and post-machined. And the post-machining you can do in the CNC hybrid, or you can do in the two-step process. So you can work in either way. And here's some more examples. I won't play these videos because I know we're short on time. Yeah, for the robotics, again, I mentioned you can go really big. So you can work with this technology in small, very delicate parts like wearables, watch bezels, for instance. We've done a lot of those. Or you can work with really large complex parts like you see here. And the other things we demonstrate with the technology is the nice thing about wire is that you can come in and pretty much work at any angle. This is a part we made here just to demonstrate you can come in at a 90-degree angle and print, and you get this really great property. We've actually done printing upside down as well. So that's something I think would be upside down would be very difficult with powder, but with wire it's no problem. Okay, almost done here. Last slide. So here's some more example of different applications. Honestly, we've got probably thousands of applications now, and it's always difficult to know what to show because we've made the technology very accessible. I think there's just been a lot of industries. I think we expected that, but we didn't expect it so fast. I think for a lot of different industries to come to us to explore the technology. So it's exciting to see, but like I say, it's so many different things to show. Sometimes it's hard to cherry pick what to show, but hopefully you've seen the breadth of the technology, and thank you for your time, and happy to be in this great event.
Okay, thank you so much for this impressive presentation. So I go with the epic question. So what you can do for the others, it's nearly very clear, but also please answer. And also what can do the others for you? So how we can set the cooperation with the epic environment?
Yeah, that's a really good question. So the first thing I would say about Meltio is that we're a very transparent company. So we'd love to get involved in applications. We'd love to get involved in strategic collaboration. My goal this year as CTO is to be involved in 24, my internal goal is 24 speaking events, sort of 2 per month on average. And the reason for that is we just want to be connected with the market, because it doesn't, if you're a systems manufacturer, it doesn't matter how good your product is. If you're not connected with the end users and you really understand at a deep level what the market wants, you will not be successful. So that is really important for me to have the finger on the pulse and work with colleagues like yourself in that regard.
So I think that there is no question from the other participant. So, Vindesh, please go ahead. You're muted.
You're muted.
Yeah.
Mute?
Hello, Brian. This is Vindesh from Laserline India. Thank you so much for your presentation. And actually, you are working on wire, which is a favorite subject for me. Until now, we have seen that most of the focus has been on powder in DED also, and very few people are actually working with wires, which is a much cleaner process. So I wanted to ask you, when you are making very big parts, how you are taking control of the heat input, because it's going to have some effect on deformation or anything. Secondly, second question is, have you tried with copper or aluminum based materials?
Okay, yeah, thanks for your question. If I just go back to my slide here, so to answer the first part of your question, yeah, control of the heat of the part is something that's critical in this type of process. So we can actually do that in a number of ways. One way you see here, see this part in the center. Actually, all of these parts, you can see that they're on this sort of rectangular bed on in this case, the positioner. But in the M450, it's the same thing, but on a smaller scale. And this is actually a cooling bed. So we can actually modulate the temperature and control how much heat we remove from the process. Because when you're making a large part, or if you're making a really dense solid, you're just putting a lot of heat into the part. So that heat has to dissipate. And so we can actually create this sort of control over the temperature gradient and then also control the removal of the heat from the process. That's had a huge effect because, for example, some of these parts, like you see here with this dome, this hemisphere, you would see you will get thermal distortions if you did not extract the heat from the process. So that's something we've done, and our material testing is been on parts that have been produced in this way. So that's a really critical thing. And then the second part of your question.
Have you tried with copper and aluminum based wires?
Yes, so we have we've tested approximately 25 materials. So we have a process where we have materials that we publish data on, where there's independent lab testing, and we have about 6 materials in that space right now. And then we have research materials, and then we have development materials. So copper, so we've actually tested a few different copper alloys, and plus pure copper as well. And the same for aluminum. So we're migrating those materials from the research space to the tested space. At some point this year, I think we'll have material data sets on both of those 2 materials. But if you look at the total materials, we've probably tested about 25 different materials as of today. So it's quite a broad range.
Okay. Thanks, Brian.
Thank you also for your question. Thanks a lot, Brian, also from my side. Now, usually, to wrap up a bit for the last minutes, I steal you 1 more minute from this meeting and fantastic discussion we had today. So the idea is that I like usually to share the conclusion basically of this meeting, or at least what were the hot topic of this discussion. And we see it here. So as you imagine, like more than 1/3 of my slide is pink, because of course, as you might imagine, of course, one thing that is really important for us was what Mandy told us. So what is needed today is all studies of all these things. Of course, there are priorities, and everyone has his own needs in different aspects, and that is what, of course, is the suggestion. So machine builders want to talk to end user like Mandy, and so from them they hear what is the highest priority and on what. And so please keep all this in mind. All these boxes are very important also for the afterwork of this meeting. Let's not forget about this, and of course, let's ask the end user to talk more like Mandy did with the machine builders and all the also providers of the components, because they can also be useful to complete the full picture. Then for process monitoring, let's go back to a bit of the beginning. This was already something that Florian mentioned in the first block of presentation. What he said, like here is a citation: which defects can I detect, how well, and with what? So this is what exactly it was the core of what According to 3D told us. And the point is, it has to be an efficient options. Otherwise, I have to see, the machine builder has to see also the advantage of implement certain monitoring processing systems. And so that is why also the monitoring process systems should talk to the machine builder as well, to find what is that is really is needed, and for which kind of parts and for which kind of work. And then we see the picture there. So According to 3D worked a lot on homogeneous texturing. So that is the beam shaping is really something relevant, and that is one application of this. But we know that with beam shaping you can really improve, and together with the process monitoring, that is something that is definitely needed. Then something very interesting question was about AI for additive manufacturing. That was really like interesting to hear. That is also something interesting for someone like LUNOVU, that was also here presenting the success story with Precitech. And why not? So this will help in multi-material processing, another hot topic we heard today, but also will help for other things to make it everything and all the process just more efficient and higher throughput. That is what we want to reach with additive manufacturing anyway, to a bit be competing on the subtractive technology, but also in general to be an effective technology for the industry. And so with this, I would say I stop sharing. I go back to the room with all of you that attended this meeting and participated so actively. I'm really proud of been here together with Antonio today, and I've been introducing you to each other maybe now, but also later on. Let's just keep in touch. If you need anything from our side, you feel free to reach out to me or Antonio. And of course, try to reach out also to each other. And please keep in mind, talk to your end user, talk to your machine builder. That is how we can go on and cooperate together. Thanks a lot to everyone, and have a nice evening or afternoon, depending on where you are. And also bye-bye to the people on YouTube. Hi, bye-bye.
Thank you so much to everybody. Bye-bye.
Thank you. Thank you.